Hi everyone. So let's start with a quick recap of what we talked about last time. So we defined what is linear programming. So it's optimization problem where you have a linear objective function and under linear constraints, right? So for example, in this example you can see we have two variables, x1 and x2. We have two linear constraints on them, 2x1 plus x2 less than equal to 4. So that is shown here by the green line, right? So this constraint means we are interested in the area below the green line, right? Similarly, the second constraint 3x1 plus 4x2 plus less than equal to 12, that is shown via this pink line, and we are interested in the area below the pink line, right? So when you want to simultaneously satisfy both the constraints, the set of points which simultaneously satisfy, that's this region, the common region below these two green and pink lines. Okay, and suppose you want to maximize this objective function x1 plus x2. So consider this red line which is showing x1 plus x2 equal to 0 right now. So as you move it up, you get higher values of x1 plus x2, right? So you want to, so now for example the line is at x1 plus x2 equal to 1. So all the points on the red line are x1 plus x2 equal to 1. So you push it as far as possible so that you still intersect your feasible region, right, which is the shaded area. So this is the last point where it leaves the where it's about to leave the feasible region. So that's our optimal point here, right? So this point in blue is our optimal point for this optimizing function. So what we had seen last time, that optimal solutions are always at the boundary whenever our optimizing function is linear, and as a corollary we get that there is always a corner point which is optimal. So if you want to find your optimal solution, it's enough to just check the corner points. But again, I mean, there could be exponentially many corners when you have n variables and many constraints. Yeah, so just checking each corner does not give you an efficient algorithm, right? Then we talked about this slight variation of linear programming problem, which is called integer linear programming. So here it's just like a linear program, linear constraints, linear objective function, but in addition you could have constraints like some of the variables or all of the variables must be integral, right? So you only allow integer values, right? And that's what is called integer linear programming. So what we saw last time, what we discussed was that there are three, there are mainly three algorithms, three kinds of algorithms for linear programming. So one is simplex method, which is one of the oldest. So it's efficient in practice but not known to be in polynomial time. There is ellipsoid method, which is polynomial time but not so good in practice, and then there are interior point methods which are theoretically in polynomial time and also work well in practice, right? And on the other hand, integer linear programming is NP hard, so we don't expect efficient algorithm for it. Yeah, so then what we said was the linear programming inherently is talking about a continuous feasible space, right? Your solution set is a continuous space. Moreover, it's a convex region. But still, we could think about applying in solving discrete problems, right? So, um, so we saw this example of minimum weight vertex cover. So you have a graph and with weights on vertices, and you want to find the minimum weight vertex cover. So here is one way to express this problem as an integer linear program. So you could have one variable for each vertex, and the variable belongs to 0 or 1, right? So it could either be 0 or 1. So naturally 1 indicates that you are going to choose that vertex. 0 means you are not going to choose that vertex as part of your vertex cover, right? Then you have this constraint for every edge. So what do we want in a vertex cover? For every edge we want at least one of the endpoints. So that we express as a linear constraint xu plus xv greater than equal to 1. So this we need to put for every edge, and then our objective function is naturally sum over all the vertices, and we take this sum of wv xv, right? So since xv is in 0 1, it's clearly summation over all those vertices which are chosen to be part of the vertex cover, and we are simply adding the weights, right? So it's precisely the weight of the vertex cover. So you can verify, or you can convince yourself that this integer linear program, the optimal value will be exactly equal to the weight of the minimum weight vertex cover, right? So it exactly captures your problem, and that kind of proves that ILP is NP hard, right? Because if you had an algorithm for solving integer linear programs, that will also give you an algorithm for minimum weight vertex cover, but we know it's NP hard, right? So we can't hope for such an algorithm, right? So next we said is can we try to write a linear program instead of an integer linear program and still get something useful out of it, right? So there is a natural way to convert it into a linear program. So one of the constraints is already linear, right? This edge constraint, and our objective function is also linear. The only problematic part is this condition that each variable is either 0 or 1. So we can replace it with linear constraints like xv should be between 0 and 1, right? So now xv can be any real value between 0 and 1. So now it is indeed a linear program. But now you might wonder that is it really useful in context of vertex covers, because now your optimal solution for this LP might take fractional values, right? So that might not be related to any vertex cover, right? So how to make sense of it? So to see a concrete example, we also saw a concrete example last time. So for this graph with 5 vertices, this would be the above linear program, right? So we'll have 5 variables between 0 and 1, and we'll have 6 edge constraints like this. So suppose all edge weights are 1, then our objective function is we want to minimize x1 plus x2 plus x3 plus x4 plus x5. And so what we saw was that the minimum vertex cover in this graph is you need 3 vertices at least, and since all weights are 1, you can say minimum weight of a vertex cover is 3. But on the other hand, if you see the linear program, the optimal value will be 2.5. So what you can see is that all variables can be set to half, right? And that will satisfy all the constraints. So that is clearly a feasible solution, and that achieves objective function will take value 2.5, right? And you can verify, you can convince yourself that this is indeed the optimal solution. There is no other solution better than this. Yeah, so here we see that LP optimal is not equal to the actual optimal weight of the vertex cover, right? So clearly the linear program does not capture our minimum weight vertex cover problem. So how is it going to be useful, right? So it turns out that nonetheless the above linear program can help us in designing an approximation algorithm for the minimum weight vertex cover problem, right? And this is not something special about vertex cover. This happens with many combinatorial problems, that you can use linear programs to design an approximation algorithm for them. Sometimes the linear program would be straightforward, sometimes it would not be that straightforward. So that part also requires some design techniques, right? How to write the correct linear program. Okay. So here is the algorithm outline. So we write this linear program for our. So we have a graph, right? So our input will be a graph with weights. So we write this linear program for that given graph, right? Number of variables will be equal to number of vertices, and the first step would be to use any standard linear programming algorithms and find an optimal solution for that linear program. Right, so let's say that optimal solution is x star, right? Now as we saw, x star might have fractional coordinates, so it might not relate to any vertex cover, right? So what we plan to do next is that we are going to do some kind of rounding on the coordinates of x star, and hope that after the rounding, so we convert it to an integral solution and hope that it will correspond to a vertex cover, right? So we'll need to design our rounding scheme carefully so that the solution we are getting indeed corresponds to a vertex cover, right? So that would be the algorithm, and we are hoping that it will give us maybe not the optimal vertex cover, but something close to the optimal vertex cover. So why are we hoping that? So you can imagine a picture like this, that so we wrote an integer linear program, right? So first we wrote an integer linear program for the vertex cover problem. So what does that mean? That means that I have a region, feasible region, bounded by linear constraints. So it looks like this, something like this, and any integral point inside that region bounded by linear constraints, any integral point there corresponds to a vertex cover, right? That's what we have seen, that any integral solution for the linear constraints is indeed a vertex cover, right? So all these integral points correspond to vertex covers, but when you find an optimal solution of the LP, it will not be among these, right? So the optimal solution for the LP will be somewhere at the boundary. So let's say it's here. So this blue point, let's say that's the optimal solution for the LP. So our idea is to round it off and go to an integral solution. Now when we do that, we must ensure that we go to an integral point which is inside the feasible region, right? Because only then it will be a valid vertex cover. So yeah, so maybe we go from this blue point to this pink point, right? And that's an integral solution, and because it's inside the feasible region, it would be a vertex cover. And because it's close enough to the LP optimal solution, we are hoping that it's also close enough to the optimal vertex cover, right? It might not be the optimal vertex cover, but we are hoping that it is close to the optimal vertex cover. Okay, so maybe the optimal vertex cover is here somewhere, right? So that's the rough idea. So let's see what is our rounding scheme. So what we are going to do is, so let's call this integral solution which we will get, let's call it, I mean, so it will represent a set, right? A 0, 1 solution, you can always view it as a subset of vertices, right? So how to construct that subset, that's what we are going to describe here. So this x star, remember that it's a point belonging to R to the V, so meaning it has one coordinate for each vertex, right? So our scheme would be that, so we want to construct a subset of vertices S such that for any vertex V, if x, this coordinate xv, x star v is greater than or equal to half, then we put this vertex in our set S, right? And otherwise, if this coordinate xv star is less than half, strictly less than half, then we don't put v in S, right? So that's how we construct our set S. So now we need to show, first thing we need to show is that S, the set S we are obtaining is indeed a vertex cover, right? So that's the first important point, that it should be a vertex cover. I mean, you can't apply an arbitrary rounding scheme and hope that you will get an integral point inside the feasible region, right? You might get something outside also, right? So you have to somehow ensure that what you are getting is inside the feasible region. So how do you prove that? So if you want to prove S is a vertex cover, that means for any edge you would like that at least one endpoint is selected, right? So either U is in S or V is in S, right? That's what we want to show. So how do we show that? So this is equivalent to showing that either XU star is greater than or equal to half or XV star is greater than or equal to half, right? So how do we show that? So that's where the constraints in our linear program should come into picture, right? So what are our constraints? So we have one constraint for every edge, right? And it says that for any edge UV, XU plus XV should be at least 1. So for any feasible solution, you can say that either XU or XV would be at least half, right? One of them must be at least half, otherwise how will you get the sum to be 1? So because our X star is also a feasible solution, right? It's an optimal solution. So in particular, it means it's a feasible solution. It satisfies all the constraints. So it must satisfy the constraint that xu plus xv star, xu star plus xv star is at least 1, right? That comes from the linear program, and you can see that this constraint immediately gives you that one of the two values must be at least half, and that proves that one of the vertices are in the set S. So it's indeed a vertex cover. Now, what is the next thing we want to show? The next thing we want to show is that S is close to or approximately optimal vertex cover, right? That's what we want to show. So that's something very interesting. So what you need to show for this is the weight of set S is not too far from the optimal weight of a vertex cover. Okay, so let's say S star is the optimal vertex cover. Now what we would like to show is that the weight of our set S is not too high, right? So we want minimum weight vertex cover, right? So we would like to show that it's not too high. In particular, it should be less than equal to some alpha times W of S star, right? So where alpha is something greater than equal to 1, right? So maybe 3 times the optimal vertex cover, or 2 times, or 1.5 times, right? So that alpha would be known as the approximation factor. So somehow we need a way to relate the weight of our set S with the weight of the optimal vertex cover S star. But if we start thinking about it, it's not clear how to do that, because we have no clue where S star is, right, and what weight it could have. Because see, I mean, you know that finding optimal vertex cover is hard, right? And probably it's also hard to guess what would be the weight of the optimal vertex cover, right? So we have really no clue about weight of S star. So how are we going to give such a guarantee that weight of S is less than equal to some factor times weight of S star? So here it gets really interesting. So what we are going to show, so we are not going to relate weight of S with weight of S star, but instead what we are going to do is we are going to relate weight of S star. So this pink point was S star, right? It was not S star, the pink point was S, right? That's the thing we got after rounding. And this X star is the LP optimal solution. So what we are going to do is we are going to relate weight of S with the optimal value of LP, right? Meaning the optimal value, the objective value achieved at X star. And why do we hope we can do that? We hope because S was obtained from X star, right? So then we can hope to relate S and X star, the weight of S and weight of X star. And once you relate the two, that would naturally give you a relation between S and S star. So why does that happen? So for that we need a simple observation. The simple observation is that the LP optimal value um, is always less than equal to the optimal vertex cover, right? So let me write it. So what I'm saying is that the LP optimal value, which is this summation WU XU star, right? So remember X star was the optimal solution. So this would be the optimal value for the linear program, summation WU XU star. So what we are saying is that this is less than equal to the weight of the optimal vertex cover S star. Now why is this true? So think about it. So this is true because we know that S star is a feasible solution for the LP, right? So whatever is the objective value at S star, right? The objective value at X star can only be lower because X star is optimal with respect to the linear program, right? So the objective value at an optimal point will always be lower than or equal to the objective value at a feasible point, right? And we know that S star is indeed a feasible point for the linear program, right? So its proof is simply that if you consider this vector X S star, right, which is 1 when U is in S and 0 when U is not in S, right? So it's the characteristic vector of S star, right? So just observe that weight of S star is nothing but the objective value at this point X S star U, right? So let me use a simpler notation. So let me call it a y vector, this vector as y, right? So I'm constructing a vector y whose uth coordinate is 1 if U is in S star and 0 if U is not in S star, right? So it's a characteristic vector of S star, and I'm just saying that weight of S star is nothing but summation WU YU, right? So it means that this is the objective value of the LP at this point y, right? And y is a feasible point for the LP, and hence you can say that the optimal value, right? So the objective value at the optimal solution is of course going to be less than equal to the objective value at any feasible point, right? So that's how you prove that your LP optimal value is always going to be less than equal to your optimal weight of the optimal vertex cover. Now once you do that, now we can try to relate the cost of the weight of R set S with the LP optimal, because we can hope to do that because we constructed our set S from the optimal solution by rounding of the LP optimal solution. So we can hope to relate X star and S, I mean their weights. Okay. So let's see if we can do that. So now we claim that weight of our constructed set S is at most So it increased. I mean, it is higher than the LP optimal, but it is not too high, right? So you want to, let's say that it's at most twice of the optimal value, which is summation WU XU star. So how are we going to prove this? So for that, let's go back to our rounding scheme. What did we do? So whenever the coordinate xv star was at least half, we put the vertex in S. So that means we are adding the whole weight of that vertex in our set S, right? But in the LP solution, it was maybe contributing only half, but in our set S, it is now going to contribute full, right? So you are at most doubling, right? For any other coordinate which is smaller than half, we are not putting it in S, right? So it's not going to contribute anything to our set S. So you see that we are at most doubling the contribution of any weight of any vertex. So that's why this bound of 2 holds. So let's try to write that formally. So the weight of set S is simply sum over all vertices in the set S, and we add the weight WU, right? Now this we can write it as equal to summation of, I mean, we can simply multiply 1 here, and what we know is whenever U is in S, XU star is at least half, right? So in other words, you can say that 1 is less than equal to 2 times XU star whenever U is in S, right? That's how we constructed our set S. So this inequality is just another way of writing XU star is at least half. So you can use this inequality and you can say 1 is at least 2 times XU star. So what you get, summation WU XU star, and the sum is over U in S, right? But you can also upper bound this by sum over all vertices, summation WU XU star. So that's the LP optimal value, right? So from here you get that weight of your set is at most twice of the LP optimal value, right? So let's write our summary. So what we proved is that the set we constructed, its weight is at most twice of the LP optimal value, and we had already observed that LP optimal value is at most the weight of the optimal vertex cover. So we can write 2 times WS star. Right? So that proves that the vertex cover we got is has weight at most twice of the optimal weight vertex cover. So that gives us a 2 approximate solution, and we can say that this algorithm is a 2 approximation algorithm. Right. So just to again explain quickly how we bounded our how did we bound our weight of our solution. So imagine this as the number line, right? So suppose this is the LP optimal value somewhere here, right? So first we observed that LP optimal is always going to be less than equal to the optimal vertex cover weight, because any vertex cover is a feasible solution. So LP optimal is always less than equal to any weight of any feasible point, and this is because it's a minimization program. and then what we said is that the set V constructed is not very far from the LP optimal. So the set V constructed may be somewhere here, right? So it's not the optimal vertex cover. So its weight might be somewhat higher than S star, right? But what we are showing is that the gap between LP optimal and the gap between our solution S, this gap is not too much, right? So we showed that this is at most twice, right? So in terms of multiplicative factor, we showed that this gap is at most 2. So that naturally bounds this gap. So I mean the gap, what we really want to bound is the gap between WS star and WS, right? So that is naturally smaller than the gap between LP optimal and WS, which we bounded by 2, right? So that's what we did, and that's how it gives us a 2 approximation solution. And interestingly, there is no known efficient algorithm which gives a better than 2 approximation for minimum weight vertex cover problem. And as I said earlier, this is not specific about vertex cover. You can use such techniques of using linear programming to design approximation algorithms for many combinatorial problems. But of course you will not always get 2 approximation. The approximation factor will be something dependent on the problem at hand, right? So just to again reiterate, to use this strategy, there are 2 parts where you need to be clever. So one is how to write the linear program, and the second is once you write the linear program, you will use some standard LP algorithms to solve it. Then how to round it off. So how to convert that fractional solution into an integral solution. That's also crucial. That's not always obvious how to do it. In this example, it worked out that a simple rounding scheme was good for us, but it might not be always true. So that's also a place where you need some design technique, right? How to do that. Yeah. So that's all about this designing approximation algorithms using linear programming. So the next thing I wanted to tell you is, so last time I said there are some special cases when the linear programming exactly captures your problem, right? So what I mean by that is that the optimal value of LP is exactly equal to the optimal value of your combinatorial problem, right? So there are a few such examples. There are not many such examples, but interestingly, for vertex covers, there is a special class of graphs for which LP optimal is always equal to the optimal weight of a vertex cover, and that class is bipartite graphs. So let's see why is that true. So we will not look at the weighted version. We'll just look at the minimum size vertex cover problem, and we'll see that in case of bipartite graphs, the LP optimal is exactly equal to the minimum size vertex cover, right? So this is the LP we will write, right? Because we want to minimize the size, we will have minimum summation xu over all vertices, each vertex variable is between 0 and 1, and for every edge our constraint is that xu plus xv should be at least 1, right? So what we want to claim is that the optimal value for this LP is equal to the weight of the size of the minimum vertex cover. So the proof is slightly non-trivial. So it won't be immediately clear how to prove that. So so here is a proof which is using some facts which you have already seen in this course. So recall the connection of, if you recall the connection of matching and vertex covers, you might remember that for any matching M, and for any vertex cover S, what you can say is that the size of S must be at least size of M, right? So why is this true? Because matching is a set of disjoint edges. So if you want to cover all those edges, you will have to pick at least one vertex from each of those edges. So that naturally gives you a lower bound on the vertex cover size, right? So this is true for any matching and any vertex cover. So this you might have seen already. Now what we are so this is not an interesting claim. I mean, this we know, but the interesting claim is that matching you can also use to give a lower bound on the optimal solution for this LP, right? So the claim is as follows: for any matching M, the LP optimal value, right, which is the LP optimal value for this LP, is at least the size of the matching, right? So that's what we are going to prove first. So why is that true? So just consider a matching, right? So matching is, let's say these are the matching edges. So you know that they don't share the endpoints, any of the endpoints, right? And now consider the constraints, the LP constraints for only the edges in the matching, right? So you can say for any edge UV in the matching, you have this constraint that xu plus xv is greater than or equal to 1. So just take the summation of these constraints over all edges in the matching, right? So when you do that, on the right hand side, the 1 will become the size of the matching, right? The number of edges in the matching, because you are taking the sum over all edges in the matching. And on the left hand side, what you will get is you will get a sum over all vertices which are involved in this matching, right, which are matched. So in particular, you can say that this is upper bounded by sum over all vertices, right? So that gives a lower bound, right? So in fact that shows that for any feasible LP solution, the objective value is at least the size of the matching M, right? So in particular, for the optimal vertex, for the optimal solution for LP, you get this lower bound in terms of the size of the matching, right? Now, okay, so we know this, the size of the matching gives a lower bound. Now we know something special about bipartite graphs. So this claim 1 is true for any graph, but for what we know about bipartite graphs is that the optimal vertex cover size is exactly equal to the size of the maximum matching, right? So that's a real non-trivial result, and you can prove it using max flow min cut. So I believe you have already seen the connection of matching with max flow, and you have already seen the connection of minimum vertex cover with min cut, right, in case of bipartite graphs. So if you use those connections and use the max flow min cut theorem, you can prove this, that size of the minimum vertex cover is exactly equal to size of maximum matching, right? And when you combine the two claims, you will get that LP optimal is exactly equal to the minimum vertex cover. So why is that true? So again, let's look at the number line. So what we are saying, so we said that matching size gives a lower bound on the LP opt, right? But we also know that minimum vertex cover is a feasible solution for LP, right? So whatever be the minimum vertex cover, that is its size would be somewhere higher than the LP optimal, right? It cannot be lower. So it could be higher or equal, right? But on the other hand, we are saying that minimum vertex cover size is exactly equal to the maximum matching size. So we are saying that these 2 points are actually equal, right? So that means all these 3 points are equal. So that in turn implies that LP optimal is exactly equal to minimum vertex cover, right? So that's how you get this, that LP optimal is equal to the combinatorial optimal you wanted. Yeah. So there are a few other examples where this phenomena happens. So like independent sets in bipartite graphs, matching in bipartite graphs, right? So in such cases, the LP optimal value gives you the exact optimal which you wanted for your combinatorial problem.